Alright, this video is going to look at work and power. Now here's our equation for work. Work is measured in joules. Work is force in newtons times the distance an object moves times cosine of the angle between the force and the distance. So we're only looking at the force that was in the direction of movement. Because as you see from this equation, if you don't move, if you have zero distance moved, then you have zero work. Now the cosine theta, as I said, its purpose, its use, the reason it's part of the equation is because you're only looking at the parallel component. If an object doesn't move, then no work is done. Also, it's really helpful when you're dealing with positive and negative, whether work is supposed to be positive or work is supposed to be negative. Okay? Because cosine of 0 is 1, while cosine of 180 is negative 1. So if your force is in this direction and your movement is in this direction, then your angle is 0. But if your movement is still in this direction, but your force is in that direction, then your angle is 180, and therefore to be negative. So if you think about force applied, right? Well, if you apply a force and it moves the object, then you're going to have work equals Fr, and you're going to take the parallel component, right? So if you apply a horizontal force and the box moves horizontally, then work equals F times R. But friction also does work on the box or object or whatever. But friction does it in the exact opposite direction, in the 180 degrees. So that would equal negative Fr. Same kind of idea with normal versus gravity. Gravity's in one direction, normal's the other. Okay? And if you're dealing with something on the surface, so for example, the box is sliding across the surface. So it's moving that way. Well, the force of gravity is 90 degrees from the movement, which means cosine of 90 is 0, so no work is done. So that's the idea, that's where that cosine theta comes in, why it's so important, because it tells you your sign and whether or not it will be 0. Now let's look at a problem. We have a sled that starts from rest and accelerates at 1.5 meters per second for 50 seconds. The sled is 30 kilograms and is pulled with a string at 30 degrees from the horizontal. Okay, so we have a sled. Gravity is acting on it. I'm going to use Fg since we're in the work unit and there's a lot of W's. Okay, friction acting against it. Normal. Okay, and then we have our tensional force broken into two components. Okay, tension cosine theta and tension sine theta. Now I'm going to find a couple of values that we're going to need later on. And a lot of times when they tell you stuff like this and give you all this extra details, you've got to do it. But I'm going to tell you right now, you're going to have to find acceleration and final position. So we can do that fairly easy. X naught x, v naught v, at. We know that we start at 0 and at 0 meters per second. So we started at rest. Our final velocity is 1.5, and it took us 50 seconds to get there. To find A is the easiest. We have initial and final velocity and time. We look for the equation without x. So that's v equals v naught plus at. Plug it in, and you get A of 0.03. Now to find the distance moved, x equals x naught, which is 0, plus v naught t, which is 0, plus 1/2 a, 0.03, t squared, 50 squared. And you get, I believe, 37.5. Oh, oops. Yes, 37.5. Okay, so we're going to need those values later on. I just thought I'd solve for them now. Now we're dealing with forces, right? So we got to find our sum of our forces. Sum of our forces in the x equals, well, on the positive, we have t cosine theta, okay, minus the y, which is force of friction. Which, if you break it down a little bit more, you've got t cosine of 30 minus 0.02, which is mu, times normal. Two unknowns. All right, so let's look at sum of forces in the y. Sum of forces in the y. You have positive, you've got the normal force, plus t sine theta, minus force of gravity, which in this case is 30 times 10, so 300. Okay, so we have our sums. Now the force in the x direction equals mass times acceleration. We're accelerating in the x. So that equals 30 times 0.3, m times a. While in the y direction, we're not accelerating in the y direction, so it equals 0. So we have n equals 300 minus t sine of 30, and t cosine of 30 minus 0.02n equals 0.9. Neither of these equations have only one unknown, but they both have the same two unknowns. And if you have two separate equations and two unknowns, you can solve for it. What you do is you take, let's say, the n in this case, so you take one of the variables, and you plug it in to the other equation. So you end up with t cosine theta minus 0.02n, and in this case, n is 300, minus sine 30 times t, which is 0.5t, and that's going to equal 0.9. So I just plugged in n, and from there, we can solve for what tension equals. T equals 5.05 newtons. Now from there we can go back and solve for normal, but I do not believe we need it, at least not right now. Okay. So, work equals FR cosine theta. So 5.05 times R. So it moved, what did we say, 37.5? We found that before. Cosine of 30. 164 joules. That's the work done on the box. Now we could also look at the work done by friction to find the total overall, because you'd subtract the two, because friction would be in the opposite direction, but we don't need to do that. Now, work in the vertical is similar but a little bit different. We just have to make sure we take into account gravity. For example, a 2 kilogram box is lifted 10 meters off the ground. How much work was done? Work equals force times R times cosine of theta. Now, in order to lift a box, you have to apply a force equal to gravity. So your force applied is going to equal mg, or Fg. So your mass times your gravity times the distance lifted times cosine of theta. In this case, cosine of theta is 1, distance lifted is 10, and it's a 2 kilogram box with acceleration of 10. So work equals 200 joules. Now if it was built up an incline, which is the second part of this question, okay, you would have an angle at which you did work at, but you would have a longer distance. So if you worked it out and did the math, you'd actually find out that the same amount of work was done for both. Now, power is the rate at which work is done. So power is work divided by time. Like velocity is the rate at which distance is covered. So velocity is distance divided by time. Power has units of watts, which is the capital W, not to be mistaken with work or weight. Physics really likes that capital W. Okay? Now, your reference table has these two equations. This FV cosine theta comes from up here. If you have work times time, distance divided by time is velocity. And I just missed the cosine theta. You can include that up there. Okay? So if you have your velocity, you can also find your power. Okay? So power is the rate at which work is done. So how fast do you get this stuff done? For example, a girl and boy race up the stairs to see which one is more powerful. The boy is 70 kilograms and makes it up in 30 seconds. If the girl is 55 kilograms, let me see. If the 55 kilogram girl was to claim to be just as powerful, what is the maximum time she should take? So her power of the boy, is going to equal power of the girl. Okay, so FR cosine theta over T is going to equal FR cosine theta over T. We don't have to worry about the angle because we just care about how far up they're going. So the force required for the boy to go up is 70 kilograms times 10 meters per second. And let's see. Oh, we don't need to know the R's because R's cancel on both sides. So that divided by T, which is 30, equals the 55 kilogram girl times 10 over T of the girl. So you solve for T of the girl, and you will get the time that she needs to have in order to be just as powerful, which is 23.57 seconds. So the boy can take 30 seconds, she has to do it in 23.57. So she has to be faster because she has less mass. So she needs to do less work. Alright, that's it.